So one thing, Don, I was listening to a conversation you had with somebody else, and you were talking about realism and the moon, and this idea that the kind of the whole interface theory and all that, and this idea that what's happening to the moon when we're not looking at it, right, and it not being rendered and all of that. So I'm interested in you talking about what on your model, what does it mean that the next appearance, so let's say the moon goes behind some occlusion or something, and then the next place you're going to see it is you can actually guess where it's going to come out next by with a model that assumes that it actually does exist and it's tracing out a particular path, right? So there's some explanatory value that you get from a model that does think that even when you're not looking at it, it's doing a set of steps that will lead it to be where when you do look at it, here's where it's going to be. So I was curious about hearing you talk about that, and then kind of Richard's side on his take on the realism of it and what the delta is between what we do see and what's actually going on behind the scenes. So
that's a great question, Mike, and I get it all the time in emails, usually with the kind of gotcha kind of attitude toward clearly you haven't thought about this one. And so it's actually quite easy. Just as long as you think about virtual reality in a VR multiplayer game, you'll get the right answer. So listen, instead of the moon, let's talk about, I'm doing Grand Theft Auto virtual reality with a bunch of people, and I see a red Ferrari. Well, in this example, the reality I'll assume is some supercomputer, right? Just for sake of argument, right? And if you looked inside that supercomputer, you would never find a red Ferrari. So there's only a Ferrari when you render it. Now, however, there's something going on in the supercomputer that's not a red Ferrari. And because of what's going on in there, it's lawful and so forth, I can use Newtonian physics intuitions to guess, if I look back, where the red Ferrari is going to be next based on the speed I saw it and the direction it was going. I can predict. So in other words, we can use all of our space-time intuitions as we should to predict where things are, and none of that affects the realism claim. But we're so used to thinking that way that we miss the logical leap that we're making. Just because it's a useful way to do things doesn't mean it's true. And the VR game really sort of brings that home. And by the way, my guess is that these questions are going to go away in less than a generation, because a generation raised on VR games are just going to go duh. I'll bring up one thing here that I've heard you talk about before, and I think is interesting as well. And it's along the same lines of what's real and what's not, and that is the distinction between living and non-living. I know you were talking with Bernardo about that, and the two of you disagreed a little bit. And usually I agree with Bernardo, but then this is one case where I disagreed with Bernardo. So it'll be fun to talk with him at some point about it. But I think there's no principal distinction between living and non-living. If you really take idealism seriously, as Bernardo does, and you take the dashboard or interface theory seriously, then the distinction that we make between living and non-living is merely an artifact of the limitations of that dashboard or that interface. And it's a useful distinction to make inside the game. But when we step back and say, is it really a principled, deep distinction that's true? No, it's just useful for the game, the space-time science game. But it's not a more deeply true thing. So I throw that out there. I don't know if I may not get any pushback from you, because I think that was your position as well.
Yeah. Do you think that is so? Okay, so in moving from, let's say, Newtonian paradigm to, say, the relativistic paradigm, do you think that entails in any sense getting closer to the actual dynamics going on the supercomputer behind the scenes, or like is there are we in fact getting closer to that at all, or is what is the arrow, if there is one there?
That's another very great and important question, and it gets to the very heart of what it means to have a scientific theory. So a scientific theory, and this is just like the ABCs, so it's very, very simple stuff. We always start with assumptions, and we say, if you grant me these assumptions, I'll explain all this other wonderful stuff. Now, clearly, a scientific theory cannot be a theory of everything because it's not a theory of its assumptions. Its assumptions are miracles for the theory. Now you can say, oh, well, I'll give you a deeper scientific theory that explains those assumptions. Indeed, that's what we do. But your new theory will have its own assumptions, which are your new set of miracles. And this goes on ad infinitum. Now, so that's, I think, just, standard, elementary philosophy of science kind of stuff. It has, important implications, but here's where I take it. I think that entails the ad infinitum I take seriously. That means that our science is infinitely far, always, from a complete theory of everything, infinitely far. Because this, it's like your kids when they're growing up to say, but why is that? Why is the sky blue? And you say, well, it's because of this. But why do photons have that wavelength? Yeah, at some point you just say they do. That's just the way it is, and you shut up. and so the game the kids play, which is why, always questioning the assumptions, is something that I think we can go on ad infinitum, and in principle we should take it seriously that we go on ad infinitum. Now, one thing that gets us psychologically on this is that we think that, of course, space-time is fundamental. So there is some assumption, it is an assumption, but it's the truth. And so we think, okay, space-time is, and we have that psychological feeling that space-time is the truth, and not, but science has moved on. Space-time is doomed. High energy theoretical physicists are saying that. And so we actually have to learn how to think entirely outside of space-time itself. So the one thing that I think has sort of kept us from really grasping how important it is that there's an infinite regress of scientific theories ahead of us. And so it's horrible for those who want a theory of everything. It's bad news. It's great for job security for scientists. That's infinite job security. But in terms, now to get to your question, Mike, I think it means that there is a sense in which Newton is not as useful in many cases as Einstein and quantum theory. But that I don't think means it's getting closer to the ultimate truth in any sense. I think at best what science is doing is giving us a description of a perspective on reality, one of an infinite number of different possible perspectives. So this is just the opposite of the theory of everything kind of attitude. You have a theory of a trivial perspective, the one that Homo sapiens happens to take out of the infinity. And my own feeling is that the one we take, which is a four-dimensional space-time kind of view of things, is probably one of the more trivial headsets. I mean, why? I mean, 4 dimensions is about as minimal as you can do and have it be functional. Why not have 10 or 50,000? Why not go to something more general than dimensions? So my guess is, we're on the dumber part of the hierarchy of headsets that are being used, perspectives on reality. So my attitude, Mike, and I would love for pushback, is that of course, as a scientist, I want us to get better and better scientific theories, but that doesn't mean that they're getting closer and closer to the ultimate truth. That just means that they're better and better descriptions of the particular perspective we happen to be looking at reality from, and making useful insights into that particular perspective, which is just one of an infinity of perspectives. So it's very, I would say it's a very humbling point of view on all this.
I can't help noticing, Don, that when you wave your hand with your fingers spread, we get a little glimpse of the reality behind the dashboard that Zoom creates there.
That's right.
Nice.
Look at that.
Nice.
The background blurring doesn't, like, oh, I can see the room he's in for a minute.
That's right. I've got a little bookcase behind me and the wall.
Which
Yeah.
doesn't have an orchid in it. So obviously we have the sort of standard way of of assessing whether one scientific theory is better than another is because the number of assumptions that it makes is less.
Yeah, Occam's razor, absolutely.
And the dream of a grand unifying theory is almost as though, you know, we just reduce the number of fundamental forces or fundamental constants or fundamental assumptions we need to make until there almost aren't any, as though it's always just like, it's just you know, assume that true is true and false is false and everything else will follow from that, you know.
That's the goal. We want as few miracles as possible
Yeah.
in our scientific theory. Ideally, I'm sure most in their heart of hearts would like no miracles at all, but that's when you look at the nature of scientific explanation, you always have to start with some miracles. Occam just says use as few miracles as possible. And by the way, this has a really important implication for how we progress from theory to theory. So
So your suggestion is that the space-time perspective might have a grand unifying theory with less miracles than those that we have so far, and we can assess the value of one theoretical framework with respect to another within that perspective of their quality.
right.
But we could have taken another perspective in which the same things might have been explained with a lot of miracles or with a little number of miracles, and there's an infinite number of perspectives we could have taken, and how many miracles we're using to explain our predictions doesn't tell us which one of those perspectives was true.
That's correct, or if not true, useful from our particular headset perspective on reality. And
Can I come back to the VR and the red Ferrari for a minute? So you suggested that the answer to I'm not looking at the Ferrari, but my model that assumes that there is a Ferrari gets a reasonably good prediction about where it's going to be next time I look. Perhaps it hasn't moved, actually. Perhaps it's still there next time I look. That's a model of where the Ferrari is.
right,
And you said, well, that's because the supercomputer has um, a law-like physics, for want of a better word for it, even though there isn't a Ferrari and there isn't any redness and there isn't any rendering happening until I look at it. I guess it feels like there's a bit of a something a little bit slippery about, well, when I modeled the Ferrari being in a new position at a particular time, was I making the assumption that that it had object permanence and that it was moving through space, or was I simply making the assumption that its behavior was law-like? So it's about the what am I perceiving when I perceive space-time? Am I perceiving space-time, or are I perceiving law-like stuff which is consistent with space-time?
and of course, the inclination of most of us, including smart scientists, is to take our perceptions of space-time as real, as object permanence. The moon really is there when no one looks. I mean, someone as bright as Einstein believed that, right? So that's what we typically do, and child psychologists tell us that's wired into us from 3 or 4 months of age. So it's not an intelligent, reasoned, intellectual decision that we make. It's something that we can't help. It happens to us at 4 months of age, and it takes a lot of education to outgrow it as adults. So yeah. So I agree that that's a good question. I think most of us just pre-theoretically and even theoretically assume the moon is there when no one looks, and that is real, and it's a real shock. So that's why idealism is such a shock to most people's sensibilities.
So let me extend the Occam's number of miracles thing to, is it possible to go meta on that and say, well, let's use a similar principle to assess the quality of taking one perspective or another. So in one particular perspective, we might find that we have a grand unifying theory that gets down to a small number of miracles, but in another perspective, would be equally, it might be equally explanatory, and it might have the same number of miracles, or it might have less. But if there was, is there really a difference between saying this theory is better than that theory within this perspective, and saying this perspective is better than that perspective? Because, you know, a theory is just taking a perspective anyway, isn't it?
Yes, and so yeah, the distinction between a perspective and a theory of a perspective is an interesting one, because it's hard to even talk about a perspective without sort of already having a theoretical idea, right, of what you're talking about. And there is at the core of all this a deep point, which is if I'm saying that no scientific theory is the final word, and we're going to have an infinite sequence of theories and an infinite number of perspectives, what is the ultimate nature of the reality that we're taking perspectives on? And my own view is we have to think of it like in terms of like incompleteness results, like Gödel's and others, that the reality, whatever it is, transcends concepts. It's so those who tell us if you want to know the truth, you have to be the truth by letting go of all concepts and face it head on. I think there's something there that's, but that's not a conceptual knowledge. That's entirely a non-conceptual knowledge, and so that starts to get to sound mystical. But it seems to me like a direct shot from what is a scientific theory.
Can you tell me more about the difference between conceptual and non-conceptual knowledge?
Well, yeah, non-conceptual knowledge would be any word you use to describe it, any predicates are necessarily wrong. Or so if you, it's like the Tao Te Ching, basically at the very first line of the Tao Te Ching is the Tao that can be spoken is not the true Tao. In other words, if you can talk about it, that's not it. And that's sort of the attitude I have now, looking at the nature of scientific theories, is reality is whatever it is. And we've conflated our little theories for true descriptions of reality. And I think that that's immodest and actually not understanding what we're doing. It's, I think a more modest position is to say theories are theories and concepts are concepts. They're human concepts, and that's not the truth.
So is that a bit like a Gestalt perception, right? It's all there all at once, and anything that you do to try and cut it up, categorize it, describe its parts, that's not it.
Yes, and in fact, now this might sound contradictory, but I'm trying to do a mathematical model to capture that kind of thing, right? So, but I'm going to be doing it in the spirit of humility, that's saying this is just a model that tries to capture that idea that there's some kind of deeper synchronicity that is non-causal and so forth. But from a perspective, it looks like there's causality and so forth. And so immediately I'll say right up front that what I'm about to say, I'm not saying it's anywhere near the truth. It's just that it's an interesting mathematical model. It helps us think out of that little, in other words, it helps us get out of a little box that we might be been stuck in. And so the idea is that there are these Markovian dynamics that are stationary. And that means that the entropy doesn't increase from step to step. It's the same entropy at every step. So there's no entropic arrow of time. But it's a
bit like saying it always was and it always will be. It's just what it is. Right?
It is what it is, and you can.
It's just a shape. It's not a process.
Run it forwards or backwards, you see the same thing. You know, long term, and but it's a theorem that if you take a perspective, you take a projection, like conditional probability on this. So it's a 3-line proof, really trivial. You get a new dynamics, a new Markovian dynamics, and the entropy will be increasing as a result of the loss of information in the projection. And so my own take is that our view from inside space-time. So, for example, of evolution, of organisms fighting for resources and competing, and the fundamental resource that's limited is time. If you don't breathe in time, you die. If you don't mate in time, you don't reproduce. If you don't eat in time, you die. Time is the fundamental limited resource. And as you probably know, I've done a lot of work on evolution. I love it. It's a wonderful, wonderful theory. There's no better theory of biological organisms inside space-time than Darwin's theory and evolutionary game theory. Having said that, I think that time is an artifact, and it's the fundamental limited resource in evolutionary theory. So I think that all of Darwin's theory, as beautiful as it is and as perfectly suited to description inside space-time, all of it is an artifact of the space-time projection. None of it is a deep insight into the nature of reality. We could have this deeper reality, and again, I'm not saying my Markovian model is reality. I'm just saying it's there as a way to help us think outside of a box. So this model shows how you could have a synchronistic, in the Jungian sense of a synchronistic system. The entropy is not increasing, no limited resources, no nature red in tooth and claw. But when you take a perspective on it, all of a sudden you get nature red in tooth and claw. You get organisms fighting. You get entropy increasing. You get Markov blankets. You get predictive processing. You get all that stuff. So what I'm saying is predictive processing, Markov blankets, and that whole way of thinking, absolutely brilliant. I'm not putting it down. It's absolutely brilliant. It works really well inside space-time, and every bit of it is an artifact of projection of a deeper system that's synchronistic and doesn't have, doesn't need predictive processing and so forth. It has no arrow of time. So I'm saying that again, not to say I'm right, just to say here's a mathematical model that can help us blow open some boxes that we might have, in our conceptual system.
So there will be a deep connection then between time, entropy, causation, right? If there isn't any time, then there isn't any cause, right? It's just what it is.
Right.
Nothing's causing anything because there aren't any events if there isn't any time.
That's right.
And there'll be a deep connection between that and where you are in time, where you are on this shape, taking a perspective and having a first person experience of it, right? There'll be some deep connection between taking a first person perspective, having a first person perspective, and experiencing a ride on this shape, right? I imagine the kind of shape you're talking about, like a high dimensional curve that, by the way, I'm thinking is probably a knot. And and the when you take a particular projection of it, suddenly it looks like there are events, there are causes, there is entropy increase, there's an arrow in time. The notion that the subjective field is the sort of the primary, I don't know what to call it because all the words use space-time analogies, right?
Right.
The primary thing.
Right.
There must be some deep connection between that assumption and this idea of taking perspectives in a way that have a particular point in time or see time as a real thing rather than a non-thing.
Yes, and I think that there is the question that comes out of your discussion there, that we experience things in space and time, but there is, you said, this first person perspective, and that just and the sort of the I am experience. I am, and it's striking that I am always only now. Nothing happens except now. So there is a sense in which we actually directly experience the fact that time is an illusion, because there is no time, there's only now. And time is something that I make up to describe the changes in my experiences now. So it's, and I, by the way, you can see I'm not terribly comfortable in this area right now. I don't have a mathematical model of the now and that kind of thing. So it's, but from a first person perspective, and also when you look at, you know, various spiritual traditions that talk about this kind of thing, there is pretty good intuitive evidence that now is all there is, whatever that might mean. And it does seem to interface nicely with the ideas that we were just talking about, that there could be a deeper synchronistic model that we could give a mathematics for that has no arrow of time. And in some sense, since there is no arrow of time, it's always now. But the
But
forms.
if I imagine this complex high-dimensional shape or curve, which represents everything that always was and always will be, and that isn't moving through time, it just is.
Right.
I can imagine projecting it, like projecting 3D to 2D, but I can also imagine a projection that is a bit more interesting, that a projection that is because the object that we're talking about is going to be fractal. So there's a possibility of a projection that's something to do with taking every other dimension from it, or taking every, like, I'm thinking about viewing it with different frame rates instead of viewing it in different spatial projections. Which is a strange thing to say since we just decided that it isn't moving and there isn't any time. But if I imagine myself moving on a complex high-dimensional curve, then my experience of that curve as I move around it is going to be varying. That I can see I'm riding on a subway train, and I can see that the carriages in front of me are doing this, or they're not doing that, depending on whether I'm going around a sharp curve or I'm going along a straight. That doesn't feel like moving, but it feels like the future and the past are waving around in front of me, right? If I'm riding on the train going around this curve. And if I change the frame rate or change the speed at which the train is moving, I could hit the same part of the curve with the same curvature again a moment later, and it would look like it wasn't waving around in front of me. It would look like it was stationary again, because I'd hit a harmonic of that curve.
Right.
That made everything look stationary again, right? So there would be multiple speeds I could travel that would make the world look non-eventful. And I'm reaching for something to make the projections you talk about, that when you take a projection of this shape, it looks like it has time, and it looks like it has events, and it looks like it has causes, and a first person way of thinking about it, and a way to make time fractal. Do that and give it back to me.
Well, so I think that's a great project, and it's quite interesting. There's some work. Have you heard of the Universe Plus initiative from the European Research Council? It's called
Yeah, I think you mentioned it before.
Yeah, Universe Plus. And what they're doing is they're finding these new timeless structures outside of space-time called positive geometries. Among them are the amplituhedron, cosmological polytopes, sociohedron, and so forth, and then some combinatorial objects called decorated permutations that classify these structures. So here they're not dynamical. They're these platonic solids, that, so if you will, although in some cases they're not polytopes, like the amplituhedron need not be a polytope. So it's a little more complicated than just, you know, polytopes out there. But these structures give rise to the correct predictions of scattering amplitudes for particle processes inside spacetime, like 2 gluons smashing into each other and 6 gluons spraying out at, you know, at some big collider. If you do that computation inside spacetime using quantum field theory and Feynman diagrams, It's hundreds of pages of algebra, millions of terms for one interaction. With these new objects outside of space-time, 3 or 4 or 5 terms you can write down by hand. You get the right answer without all the mess, and you see new symmetry, something called the infinite Yangian symmetry that you can't see inside space-time. So already, and this is only in the last 10, 12 years that the high energy theoretical physicists have discovered these structures. Published in 2013 in an archive, in 2014 in a journal, the first of these positive geometries. So it's 10 years old, basically. And so it's a brand new field, but they're doing exactly what you are asking, Richard. They're start. I mean, it's not the final word, but it's like they've taken a step outside of space-time, and by the way, outside of quantum theory. There are no Hilbert spaces in these structures. But what they're showing is that you get space-time and quantum theory both joined at the hip as a projection, and a fairly trivial projection. With the amplitude-hedron, there are these. It's a geometric object that has 3 parameters, n, k, and m, and then a matrix that you need called Z. And m for our little universe, space-time, m is 4. But this positive geometry allows m to be any positive number that you want. So what we call our universe is just the m equals 4 trivial example, one of the more trivial examples of an amplitude-hedron, that can go off to m, m could be a billion. So we're stuck with m equals 4. That's why when I say, I feel like we got cheated. We got the cheap version. Yeah, we got the m equals 4 version of the amplitude-hedron. But the amplitude-hedron itself, in the very definition of it, it says m could be any positive integer you want. And 4 is about as small as you can be, and have the thing just not be trivial. So there is efforts in the direction you're talking about, and the positive geometries, I think, are a really good thing to look at there. But I should say one other thing, maybe is slightly off the track, but I think it's importantly related, because given that we're doing all these different scientific theories, right? And I'm not saying none of them are the truth, all of them are perspectives and so forth. How do we, as scientists, actually go from one theory to another? Well, if we have a good mathematically precise theory, then that theory will give us the tools to explore the scope of that theory. And the point is, every theory, because it's not a theory of everything, there is no scientific theory of everything, because you have assumptions. Your theory, any theory, will have a limited scope, period. So there is no theory of everything. That means every theory, no exception. Einstein's theory of gravity, every theory has a limited scope. A good theory gives you mathematically precise tools to explore all the wonderful things in its scope and what it can do in its scope. A great theory gives you the mathematical tools to precisely find its limits. And that's how science, a really great theory, gives you the tools, the mathematical tools, to say when the fundamental concepts of that theory no longer hold. So in Einstein's theory of space-time, when you bring it into, say, quantum field theory, you get Einstein's theory assumes that space and time are fundamental, and that's a great assumption until you get to 10 to the minus 33 centimeters. And at 10 to the minus 33 centimeters, and 10 to the minus 43 seconds, game over for space-time. It has no operational meaning. So Einstein's theory, together with quantum theory, is a great theory because it gives us the mathematical tools to actually find precisely what its limits are. And that's how science works. And the reason I bring this up is there are many philosophers who think otherwise. There are many philosophers who would say that what I've just said is actually illogical, that I'm shooting myself in the foot. I'm making a logical mistake. And the argument, and by the way, I'm saying this because they've actually published this. So these are published. This is not just informal discussions over beer. They're published. And so they'll say, look, for example, I published with my Chetan Prakash and Manish Singh and a number of other graduate students and so forth, some work showing that evolutionary game theory entails that physical objects like organisms and resources cannot be fundamental. And so several philosophers have published articles saying, well, Hoffman, poor guy, he shot himself in the foot. I mean, and the argument goes like this: either evolutionary game theory faithfully represents Darwin's ideas, or it doesn't. If it doesn't, Hoffman couldn't use it for what he's doing. And if it does, evolutionary game theory couldn't possibly contradict the fundamental concepts that Darwin used in this theory, namely organisms in space and time competing for resources in space and time. And that last claim is where they go astray. They think that a mathematical model will never, for a good scientific theory, will never contradict the fundamental conceptual entities at the heart of the theory. And what I just said earlier was, no, that's how science progresses. A great theory actually gives you the tools to find the necessary limits, because they will be limited. And that's the point. This is not optional. Your theory's basic concepts are not true. They have a limited scope. And what science does that we haven't had before is the ability to have a theory that tells you the limits of its own concepts. So this is not a minor point. And apparently it's non-trivial enough that a lot of brilliant, actually very, very smart philosophers have made the same argument in print, that you necessarily are shooting yourself in the foot if you make this kind of argument.
But so incompleteness is just such a theory, is it not? Right. So incompleteness says, well, I'm going to give you a really nice logical argument that proves that really nice logical arguments can't tell you the whole truth.
And that's beautiful.
Mm.
That's really what is so great about scientific theories, as opposed to just verbal theories, right? Well, before science, we had verbal theories. And you could wishy-washy, move around, evade, avoid getting people. In scientific theories, that's really is mathematically precise. And a good theory, you can say, aha, Einstein, your stuff stops at 10 to the minus 33 centimeters. Aha, it doesn't work. And what can he say? Except, I don't like it, but yes. In fact, Einstein didn't know that there were black holes. Schwarzschild came back in 1916 and told Einstein, hey, your theory predicts black hole. Einstein didn't know that. And of course, black holes are the thing that ultimately are the doom of the scope of space-time. So that's an important aspect about science that apparently some philosophers, I'm not going to say all philosophers, but philosophers who've wanted to comment on my work about evolution and evolutionary game theory, they have systematically said that a mathematically precise theory of a scientific, like system like Darwin's could never contradict the fundamental concepts of that theory. And
based on the idea that no theory can prove its own assumptions, but no theory would contradict its own assumptions either.
That's right, on pain of being shooting yourself in the foot logically.
Mm.
And I'm saying, no, that misunderstands the whole scientific game at the core. The whole point of scientific theories is to give you the tools to find out the limits of your fundamental concepts. That's the point. We didn't have that ability before. We could just dodge and weave and dodge and weave. We would never figure out what were the limits of our theories. So science gives us the wonderful mathematical cure for dogmatism. If we apply the cure, of course, there are many scientists who are dogmatic, but as a field,
What?
science
Come
is
on.
not.
That can't be, no way, that can't be right.
Name one.
No, don't.
See, I think as a social field, science is non-dogmatic. It may be slow moving. It may take several centuries to let go of space-time, but I'm confident that science will let go of space-time because the evidence will become overwhelming. As you know, I think it was Planck who said that science progresses one funeral at a time. And ultimately that may be why science is not dogmatic, because the younger generation will be very happy to show that the older generation didn't know what they were talking about.
Well, and you know, Chris Fields has a slightly more positive version of that, where he says that only technologies settle arguments, right? So at some point, presumably there will be something that is irresistible because of its utility that rests on some other, you know, non-space-time, whatever, and then the new generation will put it into their little, you know, whatever, and then that's it. You know, that's the end of that.
I agree with that. Chris is a very deep thinker, and my own guess is that these positive geometries are our first step outside of space-time. As we really, I think of space-time as just our headset. It's our little VR headset that we use. In reality, whatever it is outside the headset. We're getting, in some sense, you can think of it as like the first layer of software outside the headset that's controlling our headset. Once we understand that software, we can play with the headset. I mean, if I know the software in Grand Theft Auto, I can do things that the wizard inside the game would be blown away. You know, I could take all of his tires off. I can take out of his gas. I can take the geometry of his whole space and change it however I wish, because I control the software. So my guess is that one killer app technology will be, once we understand the software outside of space-time, we won't have to travel through space-time. We can travel around space-time. Right. The nearest galaxy, Andromeda, is like 2.4 million light years. That's our nearest galaxy. Well, good luck. I mean, your great-great-grandkids won't get there, on a ship. But what if we don't have to go through space-time? What if we realize space-time is just the m=4 amplitude-hedron, and now we know, but that's a pretty trivial little, m=4 is the trivial case. We now know a little bit of the software outside, and we can now actually just change your position inside that little headset from here, from Earth to Andromeda Galaxy, and just change your pointer.
But that's very interesting, right? Because you know, the conventional theory also points out what the actionable control knobs are. So, right, so within the space-time, we know, there's mass and there's some other stuff, that those are our experimental control knobs. Do we know, if we're dumping all of that, what's the next set of practical control knobs that we get to twist?
And that now gets into the nitty-gritty of these new positive geometries. And that's only going to be a first step, because they have no dynamical systems here. These are just like static geometries. And so in some sense, and no surprise, it's only been 10 years. So I'm,
yeah.
So I think that they'll want to go there, but they are giving you some different knobs. The knobs now are the face structures of these geometries and the volumes of the various subparts of these geometries. So those are sort of the new kind of knobs, and you get things like the unitarity underlying quantum theory comes out of sort of, again, the way the faces divide into smaller faces, and you also get now I forget how this happens. You also get so you get locality also coming out from the geometry. So you locality and unitarity are something that you see directly in space-time, but they're sort of artifacts of the geometry of these objects beyond space-time. So we're going to see that kind of thing. What are the explicit knobs for us are now just part of the geometry, and there's something else that's more interesting about these bigger geometries. And what I'm trying to work on with my team is trying to get a Markovian dynamics that would give rise to these positive geometries, where we could then really start to have, to really get to your question, Mike, have different kinds of knobs that we could turn. That would be much more interesting, and actually be able to play with things like mass and momentum and energy, because we would know what those are. For example, I think mass might correspond to the entropy rate, communicating classes of these Markovian dynamics and so forth. So we have specific knobs that we're starting to propose, right? Because the standard model of particle physics has to put the masses in by hand. But if our theory says the entropy rate of a communicating class is going to project to what you call the mass, then all of a sudden we can make predictions about masses from first principles in this theory. So we will have new kinds of knobs that are predictive, whereas before we had to just put them in by hand. We'll see. I mean, this is where we're headed. I'm not saying we've done it.
I have a wacky analogy, and so this is probably pushing your video game analogy too far, but in my search for control knobs, one interesting thing about video games is that often there are combinations of key presses that unlock meta properties of the system that are not about, so you've got your controller that makes the Ferrari go faster or slower, but there's a combination of button presses that does not mean anything within the game. It's completely, it's nonsense within the game. 5 times to the left and then really quickly right, that kind of stuff. It doesn't do anything really in the game. But what it does do is unlock a meta debugger or something for the that was put in by the designers that let you tweak things for the purposes of improving gameplay. So it's like you can go in and you can change the mass, or you can whatever, right? And you unlock it with these things that have no meaning within. So I wonder if we're going to find that if we take this whole thing seriously, I wonder if in the future you're going to find there's that the control knobs are some kind of sequence of some kind of action that under the old model doesn't do anything, but actually then somehow in a meta way changes, lets you that's my conjecture, right? Is that there are going to be knobs that they're made of conventional actions, and yet they only make sense from the next level up. They don't make any sense at the level that you're looking at. So maybe that's another way of looking at, the control knobs may look, if you zoom in, they look, well, that's just the conventional, magnetic fields that we've been, but if you do this or that, suddenly it like, cracks some kind of, some aspect of the simulation, that kind of thing.
I think that's very likely, Mike. I think that's, and that again would be part of the new technology that would probably, persuade everybody that we need to move beyond space-time. I mean, one little hint in that direction is, I mentioned the m=4 aspect of the amplituhedron, and m=4 is just the meta parameter for our little 4-dimensional space-time. But there's already a parameter they found outside of space-time that you can crank it up and have a better headset. So why not an m=8 headset, right?
Yeah. The question is, what's what's the actual crank, right? And there are examples of this. So I'm here's one silly example. Like I don't know if it's silly. I'm not the something like feng shui, right? So somebody says, oh, you've got to have a corridor that looks like this, and then you'll have financial area. And you say, what the hell is the connection between the angularity of my corridor and the finance system that's going to bring in more? And say, don't worry about it. That's this is what it is. And right, so that kind of thing that only makes that doesn't make sense within the model, but somehow activates some kind of large scale meta patterns that do change how the virtual reality operates because of things you do in it.
I agree, and I think that's going to be one of the more fun, promising, and wild, probably, because we're going to have to really think outside of the space-time box. But we see, even in our current science within space-time, we get little hints of this, like that with Newtonian physics and Einstein's physics, you don't get the notion of entanglement. And all of a sudden with quantum theory, you get this thing that says you can do certain things and objects will be entangled over long distances of space. And it takes decades before we're scratching our head and we're thinking about it. Takes decades before we figure out how to actually use that knob, and all of a sudden we realize, oh, when we do it, actually, wow, there are useful things that we can do with this knob. So the math told us that there was this knob way back in 1926. It took several years for us to realize it was telling us that there was this knob, and then it took us several more decades to start figuring out how to turn the knob. And all of a sudden we're realizing, wow, that's a really important knob. So yeah, but I think that the problem is our brains have a hard time thinking out of their old boxes. Even a brain like Einstein's, I mean, he pointed out entanglement in some sense because he thought that it was wrong.
Richard, do you want to say anything about the circularity of time sort of thing, right? We've talked about a little bit before.
Yeah. Um, so I've been thinking about everything is a vibration, everything is an oscillation, and things which appear to be objects are just oscillations of particular combinations of harmonics that create um, uh, high dimensional curves. But really, all of it is just an ordinary equal curvature circle in a high dimensional space. There's no special kinks or anything in this orbit. It's just that when you project that orbit down into lower dimensional spaces, it doesn't look like a circle anymore. So, for example, when you project it down from one dimensionality to another, then it looks like it doesn't have equal curvature all over. And you regain something that looks like an ordinary regular orbit that's circular again when you find a harmonic projection that is taking a particular time slice through that temporal thing. And if the reason that I can see you is because I'm an oscillation that's at the same frequency as you, and that if we were at slightly different frequencies, you would just look like a blur to me, and I would look like a blur to you. But if we were at the same frequency, we can see each other. But I could also see you if I was at twice the frequency or half the frequency. It would, if I was at a harmonic of you, I would also be able to see you. You would look stationary in those as well, right? And then the thing that's useful about that potentially is that if I was reacting to things that you do, if I if everything that you are is an oscillation and everything that I am is an oscillation, then when I react to things that you do, that'll look like my reactions come after the stimulus. But if I do it the right amount of late, then it's as though it appears to be just before the stimulus, like wagon wheels going backwards in the strobe of the TV, right? So if everything is cyclic, then by doing a reaction that's just the right amount of late, actually becomes a prediction. And what I'm reaching for there is that when we act on future consequences that we would like to have, right? When agents appear to act, when an organism appears to act with agency, it appears to do something because it wants a particular future outcome. But what it's really doing is responding to something that has already happened in the past with just the right amount of late for it to appear to have becoming just in time in advance of it occurring again.
Yes.
But that only works if everything is cyclic. If events are really unique and time is really linear, then you don't get to do agency that way. You don't get to have anything that looks like it's in advance of the causes. So, and then you get things like nested agency, nested selves from the harmonics of the oscillations, that we're looking at the same thing but at a faster time scale, and then you get a self inside a self, that sort of thing.
Yes.
I don't know what you're supposed to make of that, but that's what I've been thinking about.
Well, I think we're on the same page. I mean, we're doing exactly that kind of, we're attempting exactly that kind of thing, where the Markovian dynamics, when you look at the asymptotic behaviors, it's characterized by the eigenfunctions of these kernels. And when you look at what they're in many cases, they're identical to like the wave function of free particles in quantum theory. So they're all about waves. The whole thing, in some sense, everything we're doing with the Markovian dynamics of conscious agents theory is all about vibes, harmonics, and ones that are compatible, ones that are not. We talked, I think, last time a little bit about this trace logic that we've discovered, and we're continuing to work on, the paper to publish on that. But that gives us a way of combining and also disunifying, so disassociating consciousnesses based on their compatibilities or incompatibilities. It's a non-Boolean logic of consciousness, and it also gets at something that you talked about earlier, which is in some sense, you talked about like temporal windows. Could we have some kind of notion of temporal windows? And we're actually looking at that in two different ways in this. We can actually take sampled chains, so we can so we can have different temporal windows of the sampling, and that will, and we actually are hoping that will actually help us in predicting, for example, the inner momentum distributions of the proton. So inside the proton, when you're at the most low resolution, what they call Bjorken X and Q squared, which is the temporal and spatial resolutions that are inside the proton, you'll see 3 dominant valence quarks. As you increase your temporal and spatial resolution, you start to see quark-antiquark pairs appearing and a bunch of gluons. And at the highest resolution, it's basically just a gluon C. You're just seeing, it's all gluons, all the energies in gluons. And we think that we can get this by looking at smaller and smaller temporal windows on our Markov chains. They'll be getting the better and better resolution of Bjorken X. And in our model, what happens is as you reduce the temporal window, you bias towards particles that look like they're massless spin 1 particle in our model. And that's just from from sampling. It just is all an artifact of the sampling. So what we're going to propose is that as we, from our model, when you're looking at the finest resolution inside the proton and you're seeing the gluon C, it's not that you're getting closer and closer to reality. You're seeing noise. You're seeing statistical noise, and you're seeing that noise as massless spin 1 particles. There we're actually hoping to take this temporal resolution idea and actually make hard-nosed predictions about the momentum distributions of particles at different Bjorken X and Q squared inside the proton. So absolutely. And we're working on another interesting idea.
But does that connect with a notion of, so if events are circular, if time is circular, then the idea of taking actions because you had an intention to produce a particular future, or taking actions because it's a consequence of a particular past, those things are symmetric now. Like we can go forwards or backwards on this circle, it doesn't really matter. And if I observe what's going on at a particular frame rate, it'll look like a prediction. And if I observe it a little bit later, it'll look like it was a consequence. So it's
yes,
looking at things at closer temporal resolution is very close to not just looking inside physically, but looking inside temporally, but also it's very close to the notion of you know, exactly the kind of thing that's weird about agency, exactly the kind of thing that feels weird about consciousness, is that this thing, like, I feel like, you know, I know that I exist now, as you say, and now is always here, and I'm always